Good afternoon, everybody, and welcome to this first CERN Colloquium of 2025. A few people are still coming from coffee. So, as many people in this room will know, long baseline neutrino experiments are key to measuring and understanding the properties of this mysterious and least understood fermion. And there's much in store at this time. Soon, in the coming years, the baton will pass from the existing T2K and NOVA facilities to a new generation of long baseline neutrino experiments centered around the Hyper-K and DUNE experiments, for which CERN is playing a critical role, particularly in the case of DUNE. So today's talk is going to delve deep into the enabling role of the CERN neutrino platform in these experiments and have a look at the ambitions and directions for the European neutrino community. Our speaker, Christos Touramanis, Professor of Experimental Particle Physics at the University of Liverpool, is a founding member of DUNE. Among his scientific achievements, he was lead analyst in the discovery of CP violation in the B system at Babar in the 90s. He was also involved, if I get my notes, analysis coordinator of the near detector for the T2K experiment, ND280, contributing to the first observation of muon to electron neutrino oscillation, and lead analyst at CP-LIA in precise tests of CPT and other symmetries. Christos led the construction of ProtoDUNE here at CERN in 2016 to 2018, and is now back at CERN, busily coordinating its second phase. Christos, welcome, and the floor is yours.
Thank you very much, all friends and unknown colleagues that you are here, and big thank you to the organizers that gave me the opportunity to talk about long baseline neutrino experiments, but not just about the technical things. I would really like out of this talk to bring out the important and enabling role of the CERN neutrino platform, and of course the main theme of the main content of my talk is DUNE and its prototype detectors, the ProtoDUNEs here at CERN. I'm pretty sure that everybody has seen Gargamel plenty of times walking up and down the campus over the years, but actually much less people have seen one of our ProtoDUNE TPCs over in the neutrino platform. So obviously we always start by the science. What's the context? Why do we do this? It has to do with understanding the neutrinos, their nature, their interactions, and measuring their parameters in the simplest case. So basically, neutrinos, there's a lot of them. They're everywhere in the universe. They are the second most abundant species after photons. They are the lightest elementary particles of matter, and actually there's this 6 orders of magnitude gap between neutrinos and the other, the charged fermions in the Standard Model. And the question is, what is that telling us? If it is telling us anything, we don't know. But anyway, even before we ask such questions, the thing is that there's no mass-generating mechanism for neutrinos in the Standard Model. There's no term in the Lagrangian. It could be through the Higgs interaction, what we used to call in neutrinos the Dirac mechanism. But in that case, there has to be right-handed sterile neutrinos, not interacting in the weak interaction. And they are not anywhere in the theory elsewhere, and they are not anywhere that we have been looking for them in experiments. Or it could be that they are their own particles, the Majorana mechanism. We don't know the mass ordering. It could be that as you go from the first generation to the second to the third, the masses get higher, as they do in charged fermions, or for neutrinos, it could be the other way around. We don't have any proof of one or the other. We actually don't even know the absolute mass values. We have the question if neutrino flavor oscillations violate CP, and that could be related or not to some leptogenesis model and then to the matter dominance in the universe or not. And then we don't know if the three generation mixing is all there is in neutrinos. Maybe there's more. And in order to do that, we are going to do unitarity tests of the mixing matrix, the PMNS as we call it. So basically the underlying things here, the mass ordering, CP violation, and the unitarity of the mixing matrix are the three main science goals of long baseline experiments, at least in the next decade or two. Now, very briefly about mixing. What we have is that neutrinos, whenever we produce them or we observe them because they interact, that always happens through the weak interaction, the only one they have, and they come in three types. But then, when they travel, they have non-zero mass. They travel in the mass eigenstate, so therefore, you produce certain weak eigenstates here, and which weak eigenstates you're going to detect over there depends actually on the mixing. As we do for quarks, for flavor mixing, you go from one basis to the other through this unitary 3x3 matrix, which is called the PMNS. In the same way we say the CKM. It's from the people who proposed it. And if you have, from simple mathematics, if you have a unitary 3x3 matrix, that has always four degrees of freedom, four independent variables. And this you can present as three rotation angles, the thetas, and one imaginary phase, which, if not 0 or pi, gives you CP violations. So you can analyze your matrix like so. Each one of these is one type of transition in the mixins. You have the usual sine-cosine notation to understand what is in there. And long baseline looks at this, the 1-3 transitions, and delta CP, but is also sensitive to the 2-3 transitions. So you can write the most simplified mixing in case of two neutrinos, which gives you the probability for mixing, and that goes with the angle theta, one of those theta angles in the matrix, which determine the size of the effect, how strong it is. And then you have the corresponding delta M in here, and L over E, the distance between where your neutrinos are produced and where they are detected, over their energy. And that determines these three things determine the frequency, the position of the minima and the maxima. And all of that until 20 years ago was in books, but now we observe them with real data. You see here from T2K on the left, we should see all this muon spectrum, the black line, because this is what we produce, and then it oscillates away over 300 kilometers, and we observe the points on the red fitted line, and the ratio of the two gives you the minimum, actually the maximum of the mu disappearance. And then in the future experiments, like, for example, in DUNE, we'll have so much more statistics that this will be determined extremely more accurately. And then down here you have the nu E, the appearance spectrum, as we measure it, again in T2K. And on the right, you see, for example, in hyper K, there will be enough precision to be able to distinguish which one of those lines we are on, which depend on the value of delta, and that's how we measure CP violation. Just a quick slide on how you make an experiment, a long baseline experiment. You get a lot of neutrinos, so therefore you need a very intense proton beam. Nowadays, you start with 1 megawatt of protons, and hopefully in 5 to 10 years we'll be at 2 or slightly above. You slam them on a special target, which will take the energy without destroying itself and the radiation. Then you focus it with 3 horns. Usually, you focus the pions, you let them decay, put a beam down to stop the muons, and you have your neutrino beam going. Somewhere here, you put a near detector to characterize what you produce, and then you go a few hundred to quite a few hundred kilometers away. You put a huge far detector underground to be quiet to be protected from cosmic rays, and you adjust the L over E. So first you choose your location, and then you adjust the energy of your neutrinos, such that you are sitting at a maximum where you have the best sensitivity. Now, that is the principle. Where do we stand internationally in the particle physics program? The P5 strategy in 2014 already defined neutrinos as one of the 5 physics drivers, and then deriving from that, there are 2 recommended large projects. One of the 2 was LBNF and DUNE. Then in 2023, there was the next P5, and there we decided that it's better to think of 6 physics drivers, one of them being the neutrinos. And then, deriving from that, we said that without a ranking, if you like, on a flat prior, 3 projects should be fully exploited from the ones in construction, one of them being DUNE, phase 1, together with High Lumi and Rubin. And then in terms for the next large projects to be constructed, DUNE phase 2 came second only to CMBS4 and 1 position above the offshore Higgs factory. And in Japan, they had 2 main thrusts in 2022 in their latest strategy that I have seen, one of them being Super Kamiokande. So we are doing quite well internationally. We are recognized as doing science which is of the highest importance. What happens in Europe in 2013 already, the strategy had 4 main bullet points at its top. And one of them was to develop a neutrino program mentioning possible contributions in Japan or the US. And then by 2020, there were these 2 bullet points about major developments from the previous strategy, and one of the 2 was about neutrinos, mentioning the neutrino platform which was in operation, repeating offshore experiments in Japan and USA. But actually this time it was not degenerate. There was a clear steer that the priority should be on realizing LBNF and DUNE, the American program. What did CERN do? Because strategies are good, but actions are better. So the laboratory in 2013 created promptly the neutrino platform project. Then 2 years later, they allocated resources, so construction of the building started. And they signed with the DOE the neutrino protocol. And 2 years later from that, they signed an addendum which defined the 2 ProtoDUNEs, the prototypes, and the contribution of CERN in the form of 1 far detector cryostat to DUNE. And then in 2022, they signed another amendment where CERN pledged to actually provide also the 2nd cryostat for the DUNE far detectors. And this is the first for this laboratory in that it contributes to both detector and facility for a project which is at another laboratory. Something which was always allowed since the lab was created, but it has never been exercised. Now, neutrinos, we don't have neutrino beams as we speak at CERN. However, neutrinos and CERN, they go a very long way in parallel, and some people might recognize quite a few of these points. I will mention the invention of the magnetic horn by van der Meer here, the device which we use to make all high-power neutrino beams, and that was already in 1961. That's quite a long time ago. 73, I would dare say that the first very big discovery of the lab was neutral currents with neutrinos on Gargamel. And then in the 80s, there were the dump experiments. In the 90s, there was Chorus and Nomad. And more recently, the CERN to Gran Sasso neutrino beam, where Opera discovered observed for the first time new tau appearance. And Icarus demonstrated large TPCs for neutrino physics, and they also did quite a lot of other very beautiful physics. So where do we stand now? Enough with history. 2 running experiments in the world, T2K and NOVA. T2K is in Japan. I am a member of that. We make a beam on the east coast at J Park, which then we shoot 300 kilometers to the west coast to Super Kamiokande, a 50 kiloton wattage Cherenkov detector, and we measure the oscillations. Our data, when fitted here for delta CP, the CP angle, for both orderings, for both mass hierarchy hypotheses, they always prefer maximum CP violation at minus 90 degrees. And actually, we can exclude at 90% level CP conservation. However, we know that this in particle physics, where we have strict criteria, it is not much. So we say that we have some hint, but at least it's nice to see. We can fit jointly the T2K beam data with the atmospherics from Super K. We gain very little extra sensitivity. However, at least the results are stable, and that at least is something nice for us. I wouldn't mention technical things about T2K, but we did do an upgrade of our near detector over the last few years, where CERN has played a very central role. What we did is that we replaced the detector which was back here in this area of the near detector We removed it and we put new things in, a super FGD, a very fine grained active target. The mechanics, a lot of the mechanics and the development for it was done at the Neutrino platform. We put new TPCs around it. The micromegas that read the charge and the field cages were also constructed in the Neutrino platform. And all the new part is surrounded by the time of flight, which was made, tested, and shipped from here straight for installation. T2K will continue taking data for a few more years before Hyper-K starts, aiming to double the statistics. And then the other experiment which is running is NOVA. That's an experiment from a beam from Fermilab to Ash River in Minnesota, 800 kilometers, so that is a very long baseline. It is a liquid scintillator technology. That's the detector. Somehow they send me that slide, and when I do PDF, the plots make a right turn. So sorry for that. They have a nice big detector, which is operating for years. They have a lot of statistics also, something like 200 oscillated nu-E and nu-E bar in total. And in terms of the mass ordering, their data prefer the normal ordering. The same thing happens in T2K. However, the significance is not very much. But when they fit for delta CP, which is the plot at the bottom, even if it's turned, you see this axis is delta CP, and the colors are for different assumptions or no assumption on the mass ordering, and their delta value is not that stable. There's not enough statistics. So basically here on the corner you have what I showed, the T2K results. This is the NOVA result alone. We have done a joint analysis taking into consideration correlated and uncorrelated systematics and all of that. We did it in the best way possible. And we come out with basically two ways to plot the combined result for delta CP. Depending on the mass hypothesis, you can have CP violation or not in the combination of the two experiments. You can also see it in 2D. Things are not stable. And actually, each experiment separately prefers with low probability, with low delta chi-squares, the normal mass hierarchy, but the joint fit prefers the inverse. It just shows you that although we have nice experiments, very good people, we know how to do it, we know what the limitations are, we know what the systematics are, but we run out of statistics. There are not enough statistics, and then just by adding things, they kind of push and pull each other everywhere. So we need experiments to give us more statistics. What an expected conclusion. Which brings me now to the next generation of experiments, the ones which are under construction, and there's two. One of them is Hyper-Kamiokande. It is essentially T2K, only bigger. Same 300-kilometer baseline, same Cherenkov detector, but almost 10 times bigger, 190 kiloton fiducial mass compared to 25 today. And in the US, we are taking a much more ambitious approach. We have a very large baseline, 1.3 thousand kilometers, that gives us much more sensitivity to the mass ordering. We go to liquid argon TPC as a detector technology, and we aim to have 40 kilotons of fiducial mass. So very briefly, Hyper-K, before we move to DUNE. Hyper-K, you make your neutrinos at JPark, same facility as for T2K. You go through the same detector. Then they are going to build what they call the intermediate Cherenkov detector, whose prototype actually, I think you can still see here in T9. It was prototyped and tested at CERN. There. And then you have the new huge detector, total water 250 kilotons, 100 meters height, almost 70 meters diameter, optimized for sensitivity to CP violation. Now, the experiment is progressing very well. All experiments in build are progressing very well. The collaboration here has 600 members, and out of them, half are Europeans. They have completed the dome a year ago, and they are now going down in the pit. And in a few months, they will have finished the 99-meter tall excavation, which is the largest single cavern in volume anywhere. They will be using 20,000 PMTs of half a meter diameter, the largest one that anybody makes, made by Hamamatsu. Already more than 10,000 have been delivered and are being tested, and they are twice as efficient compared to the ones used in Super Kamiokande. And because of the volume, there will be boxes carrying electronics for power and readout, which will have to reside inside the water. And obviously, this must be made to survive the pressure and the environment. The assembly of the electronic units and the boxes, which there's something like 1,000 of them, is one of the projects of the Neutrino platform. It will be done there. They will be tested in water, pressure tested, and then shipped ready for installation. I like to point out the contributions of CERN, because it was in my title that how this lab, which is our laboratory for us Europeans, is really supporting us, and we can count on it for the experiments we do overseas. And that brings me to DUNE, which is the main part of this talk, the deep underground neutrino experiment. The P5 report, we said some nice things about it, like the centerpiece of a decades-long program to reveal the mysteries of neutrinos, and the definitive long baseline neutrino oscillation experiment of its kind meaning what used to be called super beams, as in very high-intensity proton beam giving you neutrinos. If the physics says that we need even more statistics and intensity, then the next step would have to involve somehow muons to give us higher intensity neutrino beams. For now, we are with this. And I didn't write personally those lines, I promise. It was a bit more independent than that. So this is the collaboration in this room on Monday. We have this week a collaboration meeting. Every year at the end of January, the DUNE collaboration meeting at CERN is the one which is the one that has the highest attendance of the three that we do in the year. So there's a lot of us in here. The collaboration is more than 1,500 people, more than 600 are Europeans from a lot of countries, CERN included in the list. And this is an outline of what we are doing. At Fermilab, we will start with a proton beam at 1.2 megawatts, and hopefully in a few years we'll be at slightly above 2. Then we make our neutrinos there and have a particle detector dug into the Fermilab near the end of the campus. Then we have the 1,300 kilometers of flight for our neutrinos going 1.5 kilometers deep at the SERF facility in South Dakota, where we are building our far detectors. And I have said that the main goals, the primary goals of the experiment is mass order, NCP violation, and PMNS unitarity. But we also do a lot of other very nice physics with solar, atmospheric, and supernova neutrinos, search for new physics, and lots of other things which every time you do a nice big experiment which works well, people get clever and clever, new ideas come along, and sometime between now and, the time scale of the operation of DUNE is the same as High Lumi, or maybe even a bit more into the 40s. So before I move on to other things, I would like to show this little plot here on the right. You see that between 0 and 5 GeV, we have a pretty much flat energy of the muon neutrinos that we produced. We are on axis on the beam, and it's a wideband beam experiment. And that's important for the technology, and I will mention that later. And what you see here, the colored lines on top, is the energy spectrum of the electron neutrinos that will appear depending on what is the value, the real value of delta CP. And then there is a corresponding plot for the antineutrinos, and then by fitting all that data together, we will extract our delta CP value. But what I think is important for some discussion that will follow is the fact that we don't have a monoenergetic neutrino beam. We have a neutrino beam which covers a lot of energy all the way up to 5 GeV. So before we go to the physics, I will flash 2 slides to show the progress. Anybody who has done beach projects knows that There is the technical challenges, the R&D challenges, there's the science, which we always get more clever at doing better than what we thought a year before. But the first huge challenge is to do construction, which also costs huge amounts of money. So our underground facility is specially built for us. It didn't exist before. The only thing that existed is the shaft, which, the Ross shaft, which brings you, where am I? Which brings you here, and then everything else has been dug out from solid rock. 1.5 kilometer underground, we blasted 800,000 tons of rock and then brought it all the way up and threw it in an open cut next door. And so all the caverns and all the shotcrete inside and everything has been done. And what you can see here, one of the main caverns for the detectors, where you can see actually rails. So basically now we are installing infrastructure, rails for overhead cranes, electricity, services, and what have you. And the next step is start assembling the big cryostats there. And actually one of the tests that we have done already maybe a couple of years ago now is that we took a real detector element, a 6 by 2.5 meter chamber-like thing, the anode plane assembly, and we actually, 2 of them, we sent them from Europe all the way to South Dakota and then all the way down to where the experiment will be to validate actually our transportation methods and steps. The other thing which I think will show you that we are on a good track is the steel for the 2 cryostats. Now, the 2 cryostats are CERN contribution, as I said, and it is not fly and forget. CERN does not buy things and send them there. CERN has done all the engineering, the design, the calculations, the international call, gave them the contracts. All the steel for the 2 cryostats was made in Spain, and here it is sitting in December at the harbor in La Coruña. And over Christmas, it has been transported to the US. And now slowly, these things are arriving at Lead, at the village, which is at the top of the shaft, on large trucks. And there's going to be a lot of them. But things are there. And then we have also ordered the cold structure, which is everything that goes inside, the insulation, the membrane on the inside and everything. So CERN will actually complete all of that, do it, test it, oversee the companies, and then sort of handle the key over to the DUNE collaboration to install the TPC inside. Hopefully you got the message that we are building. I mean, what you have seen there is already of the order of 1 billion or more on real photos, and then there's a lot of other things happening in our institutes and laboratories all over the planet in real time. Now, I want to come back briefly to the energy. Now, if you are in T2K or Hyper-K, you have this green, almost monoenergetic neutrino beam at 650 MeV, plus or minus 100. And then what you see is that the black line is the total cross-section. And in this area, it is dominated at the level of 2/3 by quasi-elastic charge current. Quasi-elastic is, yeah. So the problem is that after a bit of time, it gets tired and stops. So the thing is, the quasi-elastic is the top interaction there, very nice and clean. Neutrino comes in, muon electron comes out, and then you look at the top in the picture in Super Kamiokande or later in Hyper Kamiokande. That will make a cone, that will project, it will be the projection of a circle on the wall filled with photomultipliers, and depending on the texture and the shape and the details of the circle, you can very easily say it was a muon or it was an electron, job done with Woda-Cherenkov, costs less, is maintained easier, and you can build a huge volume out of it. However, if you have the blue now, which is the wide energy spectrum of DUNE, you will have some nice events like that and easy to reconstruct. You will have the resonant in the middle, which will give you pions, protons, and your charged pions through final state interactions might become pi zeros and all kind of things. But then you also have DIS, deep inelastic scattering. You break up the nucleus and you end up with things which, if you try to reconstruct them from circles on a wall, it will be very difficult and with big uncertainties, let alone that some particles will not give circles. And therefore, a Woda-Cherenkov at 4 or 5 GeV neutrons is not a very useful detector. So in DUNE, we go with liquid argon DPC, And these are real events, it's not simulation, where the thing is red is what you see in the control room, is just what you see as the test beam goes through the argon. We pick up the charge from one of the 3 wire layers, and we just throw it on the screen without any processing. And that is the red. And actually, that is this SAMA 7 GeV pile-up. We had a high rate where you see something which must be a pion at the top, which comes in and does a double hadronic cascade. Below it, which means a little bit before in time, as the things are shifting in time downwards to the anode, there was an electromagnetic shower. And then below that, some minimum ionizing, probably muons. And that's the information you kind of look at it. Then what you see in the right is that then we do a 3D reconstruction, offline, proper reconstruction. So the blue line, which is coming at you with the red at the end, is a pion. That's where the beam enters. And then the pion goes through 4 meters of argon and then interacts. And you can see this and identify it and measure it, independent of the fact that there is a rain of muons coming down. You see them there, but you can tell and get them out. So that's end of reconstruction. And then that's also a fully reconstructed event in blue that we use from the previous run of ProtoDUNE, where we do with Pandora, we do clustering, we recognize tracks, clusters, we reconstruct energy, and then we do physics measurements. So that's what liquid argon does for you. So there's a sketch on the left, which is quite trivial. It is a TPC, so you have a cathode at some high voltage. You have an anode, usually at ground. And then you put a voltage in there for the electrons to drift, which in our case is 500 volts per centimeter. And then a neutrino comes in. You don't see anything. It produces charged particles. This one makes lines of electrons from ionization, and these then are drifted and read out at the anode. And the argon also produces scintillation light, and it is transparent to its own light, which is very good. However, it is far UV, 128 nanometers. There's no sensors there, so we have to wavelength shift it, and you'll see how we do it. So that's how a liquid argon TPC works. Depending on your vintage, you can call it an electronic bubble chamber or a 3D camera. It's the same thing. What it is technically, it is a fully active tracking calorimeter. It is homogeneous because there's nothing. It's pure argon. There's no amplification happening in the liquid, so therefore it's easier to calibrate and stable in time. But you require at least 2 things. One is very high purity. You need parts per trillion electronegative impurities, which otherwise they would eat up your electrons, and a strong electric field of the order of 0.5 kilovolt per meter. And it was proposed by Carlo, I guess, while he was taking care of the build of UA1 and the collider. The proposal for the liquid argon TPC was an EP division internal report in May 77. And even in the abstract, it says out the basics of what we have been doing since. So we have one detector principle, the liquid argon TPC, in a single phase in the liquid. And we have 2 ways, however, to make it into a real detector in DUNE. And there are technical and historical reasons for that, and risk management. One is called the horizontal drift. Basically, the cryostats are the same, 66 meters long and roughly 20 by 20. You fill them with 17 kilotons of liquid. Now, in the horizontal drift, as the name says, what you have is you have this black, which is a cathode, and then you have another cathode. And then in the middle and at the 2 ends, you have anode walls, those anode plane assemblies, APAs with wires. And then wherever things happen, your electrons drift and are collected on the APAs, on the anodes. The drift length is 3.5 meters. The voltage unit is 180 kilovolts. And you end up with 13 kilotons of active liquid argon in one of these detectors. That's our far detector 1 in DUNE, technically speaking. Then on the right, you see the vertical drift version, which was actually developed mostly here at CERN, together with collaborators from the US and France. That's done the other way around. You put a horizontal cathode in the middle, and an anode at the top and atom at the bottom, and then you drift your electrons up or down, hence the name vertical drift. You end up like this with 6 meters of drift, so you need to put on 300 kilovolts, but we have tested that. And it gives you 14 kilotons of active liquid argon. The charge readout planes, they are not wires, they are what we call CRPs. They're essentially perforated PCBs, double layers, with strips to give you the 3 layers, 2 inductions and 1 collection for the electric charge, which is drifting. Photon detectors are put outside on the wall, on the internal wall of the cryostat, and that's not enough. So we have to put photon detector units on the cathode, some of them looking up, some of them looking down. The problem being that the cathode is at 300 kilovolts, and therefore you cannot connect them with copper. So we have 2 far detectors of 2 different technologies, and we have 2 different prototypes, 2 ProtoDUNEs at the CERN Neutrino platform, where we test the 2 pretty much at the same time. So what you see here, this is a photo taken from the top of EHN1 extension. This is the very long building in Prevesen, where the north area, where the test beams are. The platform is essentially from where the crane is. That's where the building used to stop until 10 years ago. And then the platform is what is this side. It's the extension of it. It has the trenches, which are huge, because these detectors are 10 meters high, and they are fully submerged into the trench. That is so that the beams are taken to look down, and we don't throw beams out in the air past the facility. But also for safety, because if there's a leak of argon anywhere, which is heavier than air, we just get out of the trenches and we are safe. All of that was constructed in the space of a bit less than 2 years, actually. It's kind of amazing speed. It's a very nice facility, so we have the vertical drift MP02, which gets an extension of the H2 beam line. This is MP04, the one on which I have been working at various stages, the horizontal drift, and the beam line, which comes here, and thanks to our BE colleagues for designing, making, and operating. This is an extension of the H4 line, which comes in, and then at the end dives in a 2-dimension, quite interesting airplane-type dive, and comes into the TPC at an angle. Very beautiful and very nice to operate. And then what we have is that we have our control rooms up here and offices, and then we have clean laboratories, and we have storage space, computing barracks, proximity cryogenics here and over there, and all of that. And you see the vertical drift is a small picture of the detector I showed. There's the cathode in the middle, the yellow, and anodes on one side and the other, and then the other one has the horizontal cathode in the middle. Now, I will mention one system specifically because it's new, and it's an invention of our colleagues in DUNE, and we are very proud of it. The X-Arapuca. The X-Arapuca is a light trap where the 128 nanometers light, somehow we're talking about a huge volume, huge surfaces. You want single photon sensitivity. So you need big areas. How do you do that? And all of that in liquid argon, and we don't want photomultipliers. So what they do is that you put a layer of PTP on a plastic. Then below it, you put a dichroic filter, and then you put inside a second wavelength shifter. As a result, you end up with things going through into your bar and shifted to 430 nanometers, where you can detect them. But because of the dichroic filter, you get total reflection everywhere, and the light once in cannot escape, and it bounces until it meets one of the silicon PMs, which we put around, and then we detect it. It works very well. We have tested them in liquid argon, and what you see here is what we make for the horizontal drift. We put every single thing is one Arapuca module, and then you put them together on a line, and you slide them into the APA. And this is the kind of squarish module we put on the cathode of the vertical drift. On the vertical drift, because we cannot put the copper connection, we have developed our own power over fiber supply and signal over fiber readout, which is actually the easier bit. But anyway, all of this custom-made, developed in the collaboration And that's how we make it all work. Now, why do we run the ProtoDUNEs again? Because I was here in 16, 17, 18, when we built actually the first TPCs. We then operated them for a couple of years. We took data. We have done papers. It's all great. Why are we here again? The reason is that we have changed a lot of things. There's new electronics. There's new designs. There's modified designs. So basically, those two ProtoDUNE, second generation ProtoDUNEs, they are essentially what we call module 0, where we want to have a final assessment of the performance of the final design and the elements from pre-production, and we want to test everything, the integration, the stability of the system, before we start mass producing everything, or as we are starting actually, validate the CP, the installation procedures, our estimates of how much time it takes, how many people, the special tools we have designed. So basically, you know that once this is there and work, you just have to keep making to the quality that you want the elements, ship them to South Dakota, and then get your experts there, make the TPC, and it should work first thing as you turn the key, which is actually what happened with the second run of the horizontal drift ProtoDUNE almost a year ago. We have a lot of new systems like the XArapuca, first test at the kiloton scale, with its electronics and power of a fiber. The cold electronics for the readout, the 3 chips for the preamplifier, the cold ADC and the cold data, they're all brand new, and they're the ones to be used in the FAR detector. The trigger and DAQ has been completely reconfigured. We have implemented the final scheme with Ethernet readout throughout and integration of all the systems and all of that. And it all works very well. And for the first time, we have demonstrated that while we are running from the hits of the TPC in real time, we can create trigger primitives and we can implement trigger logic, allowing us to select not only based on the beam on kaons or pions, but just based on what we see in our own TPC, we can select different things. And that's how we managed to actually see neutrinos, which I will show, which was not on the plan. It was an extension of scope. So all of that works very well. And of course, you get particles, charged particles, and you do cross-section measurements. But we also demonstrate that we can also do BSM searches, should we wanted to. So the first one is the horizontal drift, MP04. This is the TPC as we did it. You see here 2 APAs, they are 6 meters high. You see the photon detectors, the XArapucas inside. Then this is the field cage. And on the right, the black surface is the cathode, which goes to 180 kilovolts. Some of the successes we had, one is that in DUNE we require a minimum of, for the FAR detector, of 3 milliseconds electron drift time, so in terms of purity, and 10 would be the ideal goal as defined in our DDR. And you see that here we got up in the middle of June to the area of 100 milliseconds, and actually there was no blip. The cryo system was amazing, designed and taken care by the CERN cryo experts. So we expect a lot, but we got even more. And actually the band is so huge because our purity monitors, they're not long enough to measure that level of purity, so basically they overflow. But we did keep for months and months a lifetime of 100 milliseconds, which is spectacular. The other thing is that our new electronics on the APAs, I mean, there you care about signal to noise, and this is the level of the noise, which is at half of the specification for DUNE, which is at 1,000 TNC. This is after coherent noise correction, but nothing else. So they behave very nicely. We have now 14-bit ADCs, more than before, in the first version of the ProtoDUNEs. And again, less than 1 per million our channels were unusable because of either being dead or problematic in the electronics in the connections. So that TPC has run very stably for 6 months, nominal high voltage, 180 kilovolts, 500 volts per centimeter, no trips, no blips, nothing. We then exercised the high voltage and took it up to 275 kilovolts, and it worked very nicely, and that's around 800 volts per centimeter, not per meter. Sorry for the mistake. We took 10 weeks of charge beams, collected 30 million triggers. We had 100% uptime because our DAQ, which was new and integrated all these new systems, it could really run for 48 hours without intervention until we changed the configuration. We integrated ionization lasers. We have two lasers, one in the TPC and one outside, that we can scan the volume with a geometry file of the TPC, which you do for alignment and energy calibration. Worked very well. And we showed for the first time that we can generate trigger primitives and make trigger logic separately from the TPC, from the charge, and separately and independently on the light system, and then you can do whatever combination you like, and also in throughput performance after the run, our trigger and DAQ reached pretty much the final DUNE, final detector specs, so we're quite happy. We have written 5 petabytes of data over half a year, which has gone up the road to EOS and then across the ocean to Fermilab. The other ProtoDUNE, the vertical drift now, is ready to start. So as I said, you have a cathode and then you have an anode. You have a cathode in the middle and anodes to collect charge at the bottom and the top. So that's a schematic of a section of it, and this is exactly what we have in the cryostat. So this is the cathode, which is a metal grid. The green things on it, and it also has some more underneath, are photon detectors, are Arapucas. And then at the top of the bottom, you have the CRPs with special, very stable, precision-made superstructure to hold them so that they don't bend. The ones at the bottom is sitting on feet on the cryostat. Now, this readout in particular, I guess you can imagine what 3 layers of wire are on the APAs. I don't show it. But this one is a bit different. So imagine that your drift volume is down here, and your electrons are coming up. So then what you put is that you put one layer of a PCB, and then a second layer of a PCB above it. The first one, what you have at the bottom, you have strips of copper running, and that is your shield to keep a clean electric field above, separate from the drift volume and the charges in there. At the back of the same, you have the first strips, which is an induction at 30 degrees, and then you go up to the second PCB, a little bit above it, and there you have the other induction on one surface, which is 30 degrees the other direction. And then you go to the top, where actually you run at 90 degrees. So that's where you get your 2 layers of induction at plus minus 30 degrees, and your third and your collection at the back, which gives you the redundancy, the stereo, and resolution of multiple combinations, and a very efficient collection. And then above it, mechanically, we have to connect, obviously, the adapter boards and the electronics, because all these channels have to be read out. So this was an idea which we have realized and tested many times. Before we go to the kiloton device, what we do is that this you see here, this is a full unit. Our units are going to be 3 by 3.4 meters. You cannot make a single PCB that big, so we make smaller ones, and then we put them together. And that is something which has been advancing over the last 3 years very fast with different iterations. And every time we have a new one, we put it in this cold box. You see here, this is a cold box where we put liquid argon. The drift is not a lot, it's half a meter. You see the cathode at the bottom. But what you do is that you immerse the whole device in liquid argon, and you really do a very realistic test. And that has sped up a lot the development. The 300 kilovolts that you need for a 6-meter drift has been proven independently, and before all of that, in the previous version of ProtoDUNE. And this are some nice pictures of the inside of the vertical drift ProtoDUNE as it was before we filled it. You see here on the left is the top drift volume, 3 meters high. It's half height because of the cryostat. You have the CRPs at the top to read the charge, the cathode in the middle, you see the grid, and then the field cage all around, and then in the middle you see the bottom, and that is with liquid, I believe, so that's so the color changes. what you see on the cameras. So this is the CRP. You see the cathode on top of you, and the field gauge all around. That here is outside is the connection of the high voltage coming in. And we started filling with argon before Christmas. And this is sometime in early January. You see the date and the time exactly. The liquid arrives here, and then a few days later, the liquid already has gone at its nominal, and now the CRPs are inside the liquid argon. And we are waiting to start commissioning, and we expect to we have asked for beams starting in June for a number of weeks to do our program. And I'm coming slowly to my end. Before I go away from it, these ProtoDUNEs and the facility that we have seen, that's the CERN Neutrino platform. However, that's not all. We also have labs in other buildings, and we have other activities. And the Neutrino platform is really what was recommended in the strategy of 2013 from CERN, to build a facility where the European community of neutrino physicists can come easily to something which is our own lab, and not to a place where it takes a huge amount of money and a lot of times on a plane to go to. And we can build up the community, do our R&D, test our ideas, and prepare our contributions so that when we go to Japan or the US, we don't go as, oh yes, in my national lab I can make something for you. We go in as a strong user community. In the LHC, I think in Atlas and CMS, the largest single national community is the US. And if you take the Europeans in Hyper-K, they are the largest community because they are exactly half, and there's more than just Japanese. But also even in DUNE, we are 600 out of 1,600 or something. So this is the list of things that the Neutrino platform has done. These things which have NP names are experiments approved by the SPS committee and the research board. So the first one was the refurbishment of Icarus with a new cryostat, electronics, and proximity cryo, which came here from Gran Sasso, was refurbished and was sent to Fermilab, where it is operating in the short baseline program. And also the platform did the cryostat and the proximity cryogenics for SBND at Fermilab. Then 2, 3, and 4 is related to DUNE. NP02, NP04 are the two ProtoDUNEs that I showed. And NP03 is a generic R&D framework, which is everything else that has to do with the DUNE technologies. Number 5 was BabyMind, a muon spectrometer for the Wagashi experiment, which is sitting under the ND280 in the same pit in Japan. It's part of T2K. And that was made here together with the University of Geneva and delivered to Japan, and it's in operation since 2017. Then there is this R&D preparation for ENUBET, the monitor neutrino beam, which I guess most people know what it is. It's a fantastic future project, and it has had demonstration runs already here, fully supported by the platform. NP07 are the contributions to the near detector of T2K, which I flashed just before, the TPCs, the FGD, the time of flight. And then number 8, the latest one, is the procurement, assembly, and testing of the electronic components for the Hyper-Kamiokande photomultipliers. And then in addition to that, as we said, the platform is designing, procuring, and delivering the cryostats for LBNF for the two modules, but also big contributions in the cryogenics. They host the compliance office of LBNF, and they lead the high voltage consortium, and they are major contributions, the CERN as a member, to the timing and DAQ, the anodes, there's a no missing, the electronics, and also the cryostat for the dark side 20K experiment at Gran Sasso. So there's plenty that has come out of this. Good use of CERN investment. And then I will finish with a case of serendipity. which is when good people recognize an opportunity and you have the capabilities detector-wise and you jump on it and you can achieve something. So basically, the background is that, as we know, there is an increasing interest in the community about searches of dark sectors and various similar beyond standard model physics. And this covers, in general, long-lived, weakly interacting particles. It covers dark sectors, HNLs, axions, what have you. And actually, all experiments which have protons hitting a target and something behind it, they do that kind of search. And it's true that we do it in T2K. NOVA does it, Microbun does it, and publishes regularly. SBND will be doing it. Icarus has done it already, and we plan it for DUNE. So if you look at the picture, this is a picture, if you like, an airplane picture from the top of the Pervesen side. So the SPS beam is coming from the corner on the red arrow, 400 GeV protons. And the neutrino platform, EHN1, is here. That's the end of the building. And if you look at it then from the top or from the side in the proper graphs, you see that you have the protons hitting the T2 target, and the two neutrino and the two NP detectors, the two ProtoDUNEs, this is looking from the top. They are illuminated with whatever gets produced, sort of one on the right side and one on the left. And if you look at it in the elevation below, whatever is produced goes mostly to the bottom. And then you say, let's assume it's not a proposal, it's not a project, it's a study. You know, people with time on their hands, even without time on their hands, they will find some time in the weekend to try and do calculations. So obviously, if we take some BSM mechanism and say if something is produced on that T2 target 700 meters later through the soil, what would appear if such a thing would scatter or decay in our detectors? And they have been doing a study on the side of things. Now, obviously, one thing you would like to test is that you make some background assumptions. What is your main background? Neutrinos in this case. Which is a bit of an irony for us, but it is neutrinos. And therefore, if you say that, okay, now let's make a trigger scheme and implement it, and see if my background levels are an order of magnitude too high or too low, so what have been calculated in all these years. Well, not these years, actually, this is months of work. And then what happened is that there is actually, with a bit of Monte Carlo, you can see that there's quite some neutrinos being produced on the target going through us. But of course, the rate is quite small, so you cannot see them in data. I don't know if we go through all of our events of all the summer, if we find accidentally one or two. However, now that we have implemented the first self-trigger of the TPC, we said, why don't we actually try to select higher energy events? And we did that. And long behold, from a few runs over a few hours, we can see these things which are very nice neutrino candidates. We haven't done, we are working at the same time. This is very recent, so it's new. We're not making any claim. I'm not going to show any spectrum or numbers or anything, because this is all going on in parallel, the simulations, the reconstruction, the studies, the validation. At some point, we should be able to make some more proper physics statement. However, I thought that at the end of the seminar, it would be nice to show that 52 years after the observation of neutral currents in Gargamel, CERN has built some very nice prototypes for neutrino experiments in the US. And in testing them with charged beams, we saw that on the side of it, we can actually see neutrinos of tens of GeV, which at first appear to be pretty much on what you would expect. But as I said, we're working on it. And you can see that, for example, the one here in the bottom, if it is a neutrino, that's electromagnetic. It could be a nu-E. You can see that this one has a very nice MIP leavings zooming out of the detector. So that's probably a nu-mu. And then you can guess what the others might be. So thank you very much.
Thank you very much, Christos, for this deep dive into the Neutrino platform and the incredible work that's being undertaken now. We have time for questions from the floor and on Zoom. Jens will be monitoring. Who wants to start? I have a quick question, Christos, on the cooperation between DUNE and Hyper-K. You know, clearly the CERN Neutrino platform is cooperating with both projects, more so for DUNE than Hyper-K. But what kind of cooperation, for example, on the cross-section measurements or hardware or future analysis cooperation between DUNE and Hyper-K is envisaged?
Oh, well, that is something which is a very interesting question, and I think that for us Europeans and for CERN is something we should consider seriously. Actually, we started discussing it. We had a 2-day workshop at the end of last week with members of the community from the 2 big experiments and beyond. One thing that I didn't mention, because obviously I had no time and I ran over, is that in addition to ProtoDUNE, to the Neutrino platform and the R&D, one thing that we have been doing at CERN since years is NA61, where we measure hadron production on our targets. We have been doing it for the T2K target, and actually this summer we ran in the beam the first prototype of the first DUNE target. And that is something which we have seen that gives us very big power in constraining the systematic. So basically that is one thing that is happening. So hadron production, we depend on North Area experiment, and I think we will be asking for more of the same in the future from both collaborations. Now, the 2 collaborations, we work in parallel in time, but obviously we are also in competition in the usual way that happens. Now, as I said, between NOVA and T2K, it took years and years to start this and make it happen, to have a joint analysis. But because now we have, instead of having the older people, before I was a neutrino physicist, who have been in whatever culture there was, in the 70s, 80s, we are now dominated in the physics by people much younger than myself, who have sort of grown up as one community on the different sides of the oceans. And one ambition that we have is to start developing this joint, the electroweak group of LEP for neutrinos. And we think that because there's a lot of Europeans on the 2 experiments, actually one thing that we might be asking through this strategy mechanism is for CERN to become a hub for that activity, so not only we can test our detectors and do R&D and do what I prepared here. There is already a small neutrino group in EP, and the people are there. They are very few, but they already lead in analysis in Icarus and in T2K, so they're on both. And I think that somehow between a small CERN group and as Europeans coming here from the 2 sides, from the 2 big experiments, we can definitely create those structures in a more efficient way than was happening before.
And in terms of the running period, the physics running period of both experiments, just roughly the projected timescales for those, what's the overlap? Which one's going to get physics first?
Well, I think being DUNE here, I risk being expelled from the collaboration. However, I think the statement, the official statements from Hyper-K, I think they have been saying the end of 17, but it is clear that they will 2027. I think they are on track to start in 28. Now, what will be the intensity and the ramp up? This obviously we don't know, because our experience from Japan is that T2K was supposed to be 3 years, 750 kilowatts, a certain POT. Now, it was unlucky with earthquakes and COVID and so on, but it took us 16 years. We are still running. We should be finished. We should be stopped already, but we now reach the intensity. So I think that they will start first, and DUNE, we want to have full detectors before the end of the decade, and definitely near detector, far detector beams, everything running in 31. So that's not a big difference, but the time scale we are thinking about coming to the precision of constraining the mixing matrix, this is at the early 40s or so. So we're talking high Lumi time scales. And I am very sure that although the Japanese also for hyper-K, the Japanese like to be very strict, say, right, you will allocate you this number of years to bring us this measurement. But as we have seen from D2K, things run longer. So I would expect this throughout the next decade to be a very active field, producing physics. And then people would be, I guess, at some point thinking of the next stages also. And it will be very nice, without CERN being the place that hosts the neutrino beams, to be able to be an equally important center for neutrino physics. That's an aspiration. That's kind of my European self saying that we should try to do it, and we would like the lab to support us.
Are there questions on Zoom? Jens, do you want to?
Yeah, we have Ben Kilminster who could come in.
Oh, hi, thanks. Thanks for the nice talk. I really appreciated it. One question. At the end, you were sort of mentioning some neutrino detection with the SPS beams. One question I had is, how does the phaser program work into the neutrino platform? Is it considered separate? I mean, phaser has seen sort of few hundred GeV neutrinos recently. So I wonder how do people think of this in terms of the neutrino program at CERN?
Yeah, that's a very good question. I think things are happening synergistically and organically. When I showed the platform, actually, in one of my slides, that photograph, which is, a photograph with my mobile phone. Let me go back to that. Yeah, so you see this is the platform. Now, you see those black boxes on top of ProtoDUNE, which are our lasers. Behind that, if you look at the lab, at the clean room, which is below the barrack there, that's where a lot of phaser pieces were integrated. It was not an official research board allocated project. Just the people came there, and because of the common interest, we basically gave them the space and a bit of support. So formally, phaser is not part of the platform. On the other hand, as I say, that is one of the things of having a big central lab like CERN, that everybody is here, and not only we talk in the cafeteria and come up with ideas, but then we can go to a lab here or there and make something happen. So yes, it is not formally linked, but going forward, I think we would like to see more and more, because there is more and more synergy, both in the technologies and in the physics community, if you like. And that's something which was one of those discussions that we had at the workshop last week.
Thank you.
Question up there? Yep, Mark.
Well, thank you, Christos. It was very interesting. Could I ask about the unitarity tests as one of the key science goals? What's the outlook for them? Because I had thought those would be quite tricky. And a second quick one, if I may, completely different. Are you still thinking of a water-based module of opportunity, and why is that useful?
Oh, well, that's another question. We have here our phase 2 coordinator, but I think that is easy and I can answer it safely. The way things have gone with the development or the funding and the P5 last year and all of that, we have 2 modules which are being constructed, and you saw them. Then there is module number 3, which per P5 must be built no matter what in any possible scenario, which must be some development, but probably not much more costly than the second detector. So there's people and groups working on that. So that will be liquid argon. Now, for the 4th detector, we would like a priori to have 4 liquid argon detectors, where the 4th one would have a much more improved technology, lower energy thresholds, bigger capabilities, and all of that. And we have programs where a lot of us are developing things like that. But of course, the way the P5 recommendation came is that when there is water-based ideas and all of that, the way it was phrased in that recommendation was that at some point, DUNE should have a big say in the decision, because whatever is implemented must be compatible with the oscillation program. Now, of course, you put another technology, you need something else in your near detector, so it's more complex than that. But also, the panel recommended that also the community at large is involved with the DOE overseeing. In reality, I don't know. I mean, we will see what comes up, what communities, how well the technologies work, where money can be coming from, because obviously you need that. So I think the statement is that whatever we put in Detector 4, a bit down the road, will be compatible with the oscillation program, so it will still contribute to the PMNS constraint, but it will also open up, through lower energies most probably, access to more physics. So it's kind of a generic answer, but it is the honest one, because as DUNE and then also on the panel, there is a lot of discussion, there has been a lot of discussion. It is a matter of realism at the end of the day. And also the physics will tell us, because once we get running and we start seeing results, there might be already very early on hints. I mean, remember theta 1,3. I remember we were starting T2K and a lot of people were showing us distributions of the number of theoretical models versus where they put theta 1,3 as an argument that T2K was useless. And with a year and a half of data, before the earthquake happened, we had theta 1,3, we had appearance. So, you know, physics will also play a role.
Any further questions from the room? Maybe then just finally, Christos, you mentioned the role of the European strategy update in the 10 years ago in this field, and you flagged a possible item that might be considered in terms of an electroweak type, DUNE Hyper-K cooperation. Is there any other sneak peeks you might, or wish lists or things from the strategy update this year that might impact the long baseline neutrino program, or is it pretty much on track? And
no, I mean, I didn't catch every single word you say through the system, but sorry. I think the question was about the future of the neutrino platform and the neutrino and the CERN support.
In what way might the European strategy update this year, the 2026 update, have some bearing and impact on what's going on?
It will, because certainly our assumption, for example, for a very simple thing, DUNE Far Detector 3, there is a lot of European momentum to be part of that, in which case we envisage a model where CERN again would support us in that sense, and that would be another addendum, and that would come. I mean, this is a technology I mentioned that the platform did the dark side cryostat, because this was an adaptation of the LNG transportation technology for ultra-high purity, which actually we developed here, we proved it, and now everybody who needs one comes here and asks. So, for example, that's a simple thing. If all of a sudden CERN says, oh, now I don't care, I walk away, then we would have a difficulty in doing that. The R&D we want to do, you can imagine that for Europeans to go and run a prototype at Fermilab compared to running it here, it's a different cost, different preparation. There is the issue of the community also, the smaller countries. Me from the UK, I could possibly go to Japan and do a test beam. But my Greek colleagues, if they were part of the program, or people from a lot of other smaller countries, in terms of number in the community and funding volume, they would find it impossible. So what we want, because we want to keep building DUNE until we have all of it, we want to keep trying out and demonstrating new technologies, which a lot of us have, devices at home, in our home labs, but eventually we want to come here and test them. Hyper-K, they will have a second upgrade of the near detector, and they would like to use the facilities of CERN for tests, and the intermediate detector. And then there will be the near detector of DUNE and the next near detector, the second phase, to have the complete original plan. And there again, we will need procuring electronics, testing them, assembling. If you like, I think that we will be asking, we are trying each one from our national input, but then also we We are working on producing a document from the workshop from all of us signed together. That is not a matter of DUNE or Hyper-K or ENUBET or something. It is that or phaser, that we all consider ourselves interested in neutrino physics, and we want CERN, which for us Europeans is our national laboratory, to keep being our national laboratory. Because otherwise, the dynamic of the European community 10 years from now will be completely different. It will downgrade a lot.
We look forward to seeing all that later in the year, of course. So if there are no further questions, let's thank Christos
We have a
again.
question in Zoom.
Oh, sorry.
Vinicius Pimentel would like to come in. Please come in with a loud voice.
Hello, can you hear me?
Yeah.
Yeah. Oh, thank you. No, I'm just curious about the Hyper-K experiment. Okay, I see it was very impressive, especially the big diameter of the PMTs you used. Do you have the information why don't you decide to use the X-Arapuca technology to assemble it? I'm thinking especially about the high structure of analog power supply and readout electronics. Do you have
Is the question why
the community don't try to use it?
Sorry. Are you asking why we don't use photomultipliers in DUNE, or are you asking why Hyper-K is not using our technology?
No, Hyper-K. Hyper-K. DUNE you was using a lot. Okay, thank you.
Sorry. Oh, well, yeah. So why is Hyper-K still using PMTs? I think, yes, thank you very much. The X-Arapuca is fantastic because it solves the problem that you have scintillation light, which is at the far UV, and you want to detect it. It's at 128 nanometers, and you want to detect it above 400. So that is what it gives to you, an efficient way over a huge area to do that. In Hyper-K, where you have Cherenkov light, you don't have an issue of wavelengths. So therefore, Arapuca's end, those huge photomultipliers, they give a big coverage. They have, I don't know, 30% or something of the whole internal surface of that ginormous tank is active. If you try to do that with our technology, A, you don't need, it's an overkill, and B, I presume it would be so complicated and expensive that, so if you like, for a water Cherenkov, photomultipliers, I think, are still considering performance, durability, price, and all of that, and experience, they are the best.
Okay.
Okay, thank you so much.
Thank you for the questions. No more. So if there's no more questions, I want to thank Christos again for a fantastic talk.
Thank you very much.
And thanks to everyone else.